Hello everyone, welcome to online video lecture series developed by Jawaharlal Nehru Technological University Kakinada in association with Andhra Pradesh State Council of Higher Education. This is Dr. M. Prem Kumar, working as professor in the Department of Electronics and Communication Engineering, Sri Vishnu Engineering College for Women, Bhimavaram. Welcome to online video lecture series. In today's lecture, we will be discussing about introduction to correlation. Today's lecture, we will be discussing about the correlation between the signals. The correlation between the signals is a measure of similarity or relatedness between the waveforms. This correlation expresses how one signal is related to the time delayed version of the other signal when scanned over time axis. So let us consider a complex signals f1 of t and f2 of t, which may or may not be periodic or not restricted to a finite interval. Okay. The average cross correlation or correlation between f1 of t and f2 of t is related as r1 2 of tau. This is defined as limit t tends to infinity. This is 1 by t integral minus t by 2 to plus t by 2. This is f1 of t and this is f2 star of t plus tau dt. This represents the shift of function f2 of t by an amount minus tau, that is towards left. A similar effect can be obtained by shifting f1 of t by an amount tau towards right. Hence, the correlation may also be defined as r12 of tau is equal to limit t tends to infinity 1 by t integral minus t by 2 to t by 2. So f1 of t minus tau and f2 star of t dt. We are shifting f1 of t towards right, and for the previous equation f2 of t towards left with respect to same time constant tau. If so, f1 of t and f2 of t are periodic with same fundamental period capital T, the correlation is defined as R12 of tau is equal to 1 by t integral minus t by 2 to plus t by 2 f1 of t and f2 star of t plus tau dt. Similarly, R12 of tau, similar effect can be obtained by shifting f1 of t towards right minus t by 2 to plus t by 2 f1 of t, not f1 of t, and this is f1 of t minus tau into f2 star of t dt. So that is, so f2 of t shifted towards left to left, and f1 of t shifted towards right. So let me give some example of waveform. Suppose this is one signal which is periodic in nature. Period will be capital T. This is a fundamental time period. This is f1 of t. And second signal may be f2 of t, which is also periodic with the same fundamental time period with a different shape. So here from this point to this point, this is the fundamental time period. Tau is the shift. How much f1 of t and f2 of t shifted towards right or towards left. Now if f1 of t and f2 of t are of finite energy signals, then the correlation is defined as R12 of tau is equal to integral minus infinity to plus infinity f1 of t f2 star of t plus tau dt, and the same effect can be obtained by shifting f1 of t towards left, that is f1 of t minus tau into f2 star of t dt. Finite energy signal means signals are aperiodic in nature. Now we will be discussing about tau. Tau is a searching parameter or scanning parameter. The parameter tau is needed to find the maximum possible correlation between waveforms. Actually, two waveforms have no correlation when tau equal to 0. So that is no delay between them. And they have significant correlation by adjusting the suitable value of tau. The correlation increases as the delay parameter tau increases, and it is maximum for tau is equal to tau naught. Thus, tau, a scanning parameter which corresponds to the maximum possible correlation between the two signals. So, if two signals are signals are uncorrelated. So, in that case, R12 of tau is equal to 0 for all values of tau. So, in that case, this is R21 of tau is equal to 1 by t integral minus t by 2 to t by 2. This is f1 of t plus tau. This is f2 of t dt. and which is also equal to R12 of minus tau, where R12 of minus tau is equal to 1 by t integral minus t by 2 to plus t by 2 f1 of t and f2 of t minus tau dt of correlated signals. Let us consider two signals f1 of t with power s1 and f2 of t with power s2. We have to find the power of the combined signal of two signals. So that is f of t is equal to f1 of t plus f2 of t. Since the time delay does not affect the normalized power, the power of f2 of t and f2 of t plus tau is the same. So the normalized power S1 comma 2 of the combined signal is given by S1 comma 2. So combined signal is f of t is equal to f1 of t plus f2 of t plus tau. Let us calculate this S1 2 of is equal to 1 by t integral minus t by 2 to plus t by 2 f square of t dt. So this is equal to 1 by t integral minus t by 2 to plus t by 2. In place of f of t, you have to replace this s1 f1 of t plus f2 t plus tau whole square dt. Now you have to expand this. This is 1 by t integral minus t by 2 to plus t by 2. This is f1 square of t plus f2 square of t plus tau plus 2 into f1 of t into f2 of t plus tau into dt. Now if we expand this, this is s1 comma 2 equal to 1 by t integral minus t by 2 to plus t by 2. This is f1 square of t dt plus 1 by t integral minus t by 2 to plus t by 2 f2 square of t plus tau dt plus 2 by t integral minus t by 2 to plus t by 2. This is f1 of t into f2 t plus tau dt. So this is equal to s1 comma 2 equal to this is nothing but the power of the first signal S1 and this is the power of the second signal because time delay will not change the power. So this is equal to S1 plus S2 plus and this is something similar to the correlation between f1 of t and f2 of t. Now this can be written as 2 into r1 2 of tau. So the power of two correlated signals is equal to the sum of powers of each individual function plus twice the cross correlation between them. This is first point. Then this is first point. And coming to the second point, if the signals f1 of t and f2 of t are uncorrelated, then r1 2 of tau is equal to 0. In this case, the powers of the combined signal is equal to the sum of the powers of the individual signals. So S1 comma 2 is equal to S1 plus S2. Now coming to the third point, the signals correlated by DC components are considered as uncorrelated because DC components are rarely of interest for correlation to be considered. Consider a two uncorrelated functions, uncorrelated signals, that is f1 of t and f2 of t. If the DC components for f1 of t is f1 and f2 of t is f2 are added to this, now this is f1 of t is equal to f1 of t plus and capital S1 is the DC component. Similarly, f2 of t is equal to f2 of t plus this is another DC component. It can be seen that the correlation between the function or two signals, this is R12 of tau is equal to F1 into F2. This correlation is due to the DC component and hence the spark signals considered to be uncorrelated.